Okay, this is the seventh installment of notes on the chemical reaction engineering series. I want to talk a little bit today about reaction orders and then do some examples that pertain to second order reactions. Probably many of you already have a good idea what it means for a reaction to be first order, second order, even half order. Reaction orders can be defined for elementary or non-elementary reactions. The formal definition of a reaction order is this quantity given here. So if you have a given reaction rate, you take its logarithm and you plot that against the logarithm of the concentration of a species involved in that reaction, then the reaction order for that species is the derivative of the log of the reaction rate versus the log of the concentration. And what you're doing is you're holding the temperature and the concentrations of other species constant when you do this. The derivative of the logarithm of the rate with respect to a particular reactant gives you that reaction order. Note that this doesn't always have to be an integer, but for elementary reactions it is an integer. And we will just talk about elementary reactions right now, but remember that later in the class we will encounter cases where the reaction order can be 1/2, 3/2, 5/2, -1/2, all kinds of different things can come up to be reaction orders. So for the elementary reaction, N2O5 goes to NO2 plus NO3. This is one that we were working with last time. This reaction is first order in N2O5. It's an elementary reaction. The reaction rate is K forward times N2O5 concentration. If I think about the derivative of the log of this reaction rate with respect to the log of the N2O5 concentration, the log immediately splits into two terms, log of Kf plus the log of the concentration. Of course, the log of Kf is independent. It's a rate constant because it's independent of concentration, and so that derivative is 0. The other term, the derivative of the log of the concentration with respect to the log of the concentration, of course that's 1, and so that gives us that the reaction is first order in N2O5. Another example, slightly more difficult perhaps, is the elementary irreversible reaction A plus A goes to products. So this is second order in A because the rate law, if this is an elementary reaction, must be K forward times the concentration of A squared. So when you take the log of the rate, you get the log of K forward, which is concentration independent, and that term vanishes. You also get the log of A squared, which is equivalent to 2 times the log of A by the properties of logarithms. And so this derivative then, the derivative of the log of A squared with respect to the log of A concentration is just equal to 2. So the reaction then is second order in species A. Now it's common to take this one step further and refer to reactions like A plus B goes to products. We haven't talked about that one yet, but that one would turn out, if it was an elementary reaction, to be first order in A and first order in B. And it's common to refer to this as an overall second order reaction because it's first order in 2 reactants. Okay, so you will see some of this in the literature, and remember that sometimes reaction order refers to this overall reaction order, and sometimes it refers to this formal definition restricted to specific species. So in Fogler's book, he analyzes this reaction A plus A goes to products. It's the standard elementary model for a bimolecular reaction. The rate is that for an elementary reaction, K forward times the concentration of A squared. This should have a rate in units of moles of reactions per volume per time. For a constant volume batch reactor, we would include the stoichiometric coefficient to keep track of the fact that every time this reaction occurs, 2 moles of A are being consumed. So that's why we have a -1/2 here, consumed, and it's consuming 2 moles. We also have our rate expression over here on the right. If we integrate this from an initial concentration at time t equals 0, we find a integrated rate law that is 1 over A equals 1 over the concentration of A initially plus K times T. So this is the form of an integrated rate law for a second order reaction. Now compare this to the form of the integrated rate law for a first order reaction, which was the log of the concentration of A over the initial concentration of A is minus KT. So that's our first order integrated rate law. And then if a reaction happens to be zero order in a component A, then the rate would be the integrated rate law would be the concentration of A as the initial concentration of A minus just a linear dependence on time that this thing is gradually being consumed. So the hallmarks of these you can recognize on very simple plots. You can check for zeroth order behavior by plotting A versus time and looking for data that's scattered around a straight line. You can look for first order behavior by plotting the log of A over A naught and versus time and looking for, again, data that's scattered around a straight line. Of course, this is a straight line on a nonlinear axis. You can finally check for second order behavior by looking at 1 over A versus T, and again, you should see data scattered around a straight line on this nonlinear axis. So bimolecular reactions quite often are second order in the sense that they are first order on two separate reactants, so overall second order. An example would be a reaction with the stoichiometry like this, A plus B going to C. If this is an elementary reaction, then elementary irreversible reaction, I should say, then it will have a rate that is equal to a forward rate constant times A concentration times B concentration. It would be a mistake to write that the reaction is, it would be a mistake to write that this reaction rate is equal to the negative of the derivative of the concentration of A with respect to time if this reaction is happening at constant pressure. The reason is because the reactants will be contracting actually as the reaction proceeds. So I've written volume expansion here, but actually that should be a contraction if I'm going from A and B to a single product C. Okay, so here what we can do more generally is write our rate constant expression. The right side is perfectly fine, so I can put in K forward times concentration of A times concentration of B over here on the right. But on the left-hand side, I have to keep track of the fact that the number of moles of A are changing and also the volume is changing. And they aren't changing in any constant concentration kind of way. Okay, so we have to keep track of those two things separately. So the volume itself now is going to be a function of time. We can write a lot of these characters in this equation in terms of these separate variables. We have the number of moles of A divided by the volume is equal to the concentration of A. We can likewise define the number of moles of B divided by the volume as the concentration of B. And now that means that our equation is going to simplify to this form. Notice that before we had some concentrations on the right in A, we had volume in the denominator. We're now writing everything in terms of number of moles of each species and a separate volume parameter. Now we can still relate all three of these variables, V in B and in A, to a single extent of reaction variable. Okay, so the way that's going to work is that we start with our three species. We have their initial concentrations, Na0, Nb0, and Nc0. After the reaction has gone on for some time through an extent of reaction xi, we have Na0 minus xi, Nb0 minus xi, and Nc0 has actually gone up to Nc0 plus xi. The net, the total amount of stuff in the reactor then will be Na0, Nb0 plus Nc0 minus xi. So using this then, we can express, if we use the ideal gas law, we could say that the initial amount of material was just the sum of these three. The final amount of material is the sum of these three minus xi. That's our contraction. And so the new volume is equal to the original volume times this ratio of N0 of the sum of the initial concentrations minus xi divided by the sum of the initial concentrations. Okay, so this is really just a statement of the ideal gas law. It's a good approximation as long as we're working with gases at low temperatures and fairly low pressures and fairly high temperatures. So the result turns out to be somewhat complicated, but still solvable ordinary differential equation for the extent of reaction as a function of time. And so this is the actual ODE that you would have to solve. Probably you would have to do this numerically because it's now a pretty complicated thing. But still, you can see here that this is just a first order equation that gives you xi as a function of time. From xi as a function of time, you can go back and you can compute the amount of each species as a function of time and the concentrations as a function of time by plugging in the expression for volume in each concentration. Okay, let's say a little bit about excess reagents and bimolecular reactions. So let's go back again to this reaction A plus B goes to C. And let's suppose that we are again looking at the case where these gases are at constant pressure. We already showed that this is the reaction that actually governs the extent of reaction as a function of time. Now let's suppose additionally that one component, say component B, is in large excess relative to A. Then what that means is that you have far more B than A and C, and also far more B than any possible extent of reaction, because before the extent of reaction can get large, you will run out of the reactant that's driving that, the reactant that's being consumed. Okay, so all of these things then are going to be much smaller than the B concentration. And under those conditions, the equation here that I've starred actually simplifies to a simpler form. It gives you this equation, right? So V0, I'm assuming that this ratio is basically 1 because I'm taking something big, subtracting something small, and then dividing by the big thing again. Okay, so that ratio has basically vanished from the problem and left me with just the derivative of the extent of this reaction 1 is equal to K forward times NA0 minus the extent of reaction and NB0 minus the extent of reaction. We can further go on and divide by V0 squared and get an equation that looks like this. I've redefined my variables now that xi1 is xi2 is equal to xi1 divided by V0. V0 is just a constant. So the only thing that's really happened here is that my extent of reaction variable no longer has units of moles, but now it has units of concentration. Okay, so xi2 is this concentration version of an extent of reaction variable. And so what we get after simplifying everything and grouping terms is that d xi2 with respect to time is equal to the forward rate constant times the concentration of A at the initial time minus xi2 multiplied by the concentration of B at the initial time minus xi2. Okay, so this, interestingly, is the same equation that we would have obtained if we had treated the problem from the outset as though it was happening at constant V, constant volume, instead of constant pressure. And that's kind of interesting. It makes sense because basically if you have one component in huge excess relative to all others, then even if it's a gas phase reaction and you're at constant pressure, you will see really negligible volume expansion because the amount of conversion that can happen is very small. Okay, so that's basically the idea here, is that in that case you can just work with the problem as though you're at a constant volume reactor and everything is basically the same. So one last little tidbit on excess reagents. When you have pseudo first order kinetics, so we're going to talk about pseudo first order kinetics and how they really arise from having one reagent in large excess. Okay, so we already showed that for all practical purposes, when we have one component in large excess, regardless of whether the reaction is happening at constant pressure or constant volume, for this A plus B goes to products reaction, we can write that the rate law and set it equal to minus dA dt. The reason for this was because B was basically a constant, and it also made the volume very nearly constant over the course of this reaction. If we further say that because B is a constant, as A is being eliminated, then for all practical purposes we can say that B is just equal to its initial value. We can then group the K forward and the initial concentration of B into one roughly constant term. We'll call that K apparent. It's not a true rate constant. It's a product of a rate constant multiplied by a constant concentration. But it now will appear to have first order kinetics this thing just is going to have units of inverse time, and when I multiply it by a concentration, I get my volumetric reaction rate. Okay? So using a large excess of one reactant allows us to isolate the dependence of the rate law on the other species. For example, here we basically flooded the system with B, and by doing that, all that's left on the right that's really changing appreciably as the reaction occurs is the concentration of the other species A. Now, if this was a first order reaction, we would be able to plot this versus plot the log of A versus time and see a straight line, for example. If it was second order in A, this would be also a good way of seeing that, because we would just be able to use our standard rate law expressions for the elementary rate laws, and we could plot, for example, in that case, 1 over A versus time and see a straight line owing to the second order dependence on A. Okay, so flooding is a common experimental strategy for identifying how a reaction depends on different limiting reagents, right? So we create situations by using large excesses of one reagent where we can basically read off the reaction order with respect to the other reagents. And also, it actually is a good way of also identifying rate constants. If I know how much B I put in, and I know the first order decay constant, I can go back and back out the K forward, and then use that for other situations.